Welcome to Math with Professor V. This is video lecture for section 5.3 for business calculus on higher derivatives, concavity, and the second derivative test. So what do we mean by higher derivatives? Well, basically, we've learned how to take a derivative or find a derivative of a function, namely the first derivative. But if we keep applying that process, then we can find higher order derivatives. So typically, we won't need more than 2 derivatives in this course, but you could keep on going. And we have different kinds of notation, again, depending on the style that you're going to use to denote your derivative. So we've got second derivative being written as f. We usually say double prime of x. So you got 2 little tick marks to show that it's the second derivative. This other notation, the 2 goes after the d in the numerator and after the x in the denominator. And you might say, why in the world is that? Well, remember, the first derivative is dy dx. Yeah, that's another way to indicate you're taking the first derivative. And if we take a second derivative with respect to x, we're differentiating that with respect to x. And so what happens is basically you can say, we've got 2 d's in the numerator. And then you're differentiating with respect to x twice. So we put it after the x in the denominator. Okay? And then this last notation you'll see more often in like multivariable calculus class where you have capital D as your derivative with respect to x, and then this 2 means it's the second derivative. And then here's your function. This one's not so popular. This one you'll see most of the time we'll write f double prime, okay? The third derivative can be written in a similar way. You'll see f triple prime, these become 3's. And then once n is greater than or equal to 4, usually we stop writing a bunch of tick marks. Sometimes you'll see Roman numerals, but usually we'll just put like a 4, a 5, a 6, etc. Okay, but we're just going to call it at 2 derivatives most of the time. So let's just find f double prime for each of the following functions. And then once you have f double prime of x, we're going to substitute in. So we're going to evaluate f double prime of 0 and f double prime of 2. All right, here we go. So we need to find f prime first. So first derivative is going to be negative 4x cubed plus 21x squared. Good. And then the next term, when I bring the 2 down front, it's going to cancel with the 2 in the denominator. So this is just going to be minus 1x. Very nice. Okay. So one more time. So we get the second derivative. So f double prime of x is going to be negative 12x squared plus 42x minus 1. Perfect. So that's f double prime of x. Got that part taken care of. Then we need f double prime of 0 and f double prime of 2. So f double prime of 0, everything's going to be 0 except the last term. So it's negative 1. And then f double prime of 2, let's see, negative 12 times 2 squared, that's 4. Plus 42 times 2 minus 1, that's negative 48 plus 84 minus 1, 35. Good? Should we check it or do we feel good? Negative 48 plus 84 minus 1. Beautiful. Look at us go. Okay. Let's try something a little more difficult than a polynomial. F of x equals the square root of 2x squared plus 9. So if you want to rewrite this, I recommend it as 2x squared plus 9 to the 1/2 power. That'll be good because we got to use the chain rule. Yes? So first derivative, f prime of x. You bring that 1/2 down front and the new exponent's negative 1/2. Don't touch what's inside. And then now by the chain rule, I'm going to multiply by the derivative of what's inside. So what's the derivative of 2x squared plus 9? 4x. Very good. Oop. And then from here, let's clean up. Because 1/2 times 4x, that's just 2x. And then now I can rewrite 2x squared plus 9 to the negative 1/2 as square root 2x squared plus 9 in the denominator. So that's the first derivative. We need one more. So we got to go use the quotient rule now. Here we go. F double prime of x is going to be low d high minus high d low over low low. So low is the denominator. rad 2x squared plus 9. d high derivative of the numerator is 2. Minus high, the numerator, times derivative of the denominator. So rad 2x squared plus 9 is 2x squared plus 9 to the 1/2. We already actually did its whole derivative. It's right here. The derivative of the denominator is this. So I'm not going to redo it. I'm just going to write it out. It's 2x over rad 2x squared plus 9. And then low, so the denominator squared, which is just going to be 2x plus 9, no more square root sign. Okay? Now, we have to clean this up because it's a complex fraction. We've got a fraction inside of a fraction. Let's just make it a little neater, and then I'll show you what to do. So f double prime of x, what I would do is put that 2 in the front of the radical. So 2 rad 2x squared plus 9 minus, hold on, this is too crooked. What is going on, people? Better. I have 2x times 2x, so that's 4x squared over rad 2x squared plus 9. And then I have 2x squared plus 9 in the denominator. Now, what's causing me grief? What's giving me trouble? This rad 2x squared plus 9. That's the denominator I want to get rid of. So you multiply everybody by what you want to get rid of. Rad 2x squared plus 9. And then also down here. You have to do it top and bottom. That way you're just multiplying by 1. So you're not doing anything illegal. The math police, you don't want them after you. Okay, now this is going to distribute to the first term in the numerator and to the second term. So when you have rad 2x squared plus 9 times 2 times the same radical, the square roots cancel out. So then you just have 2 times 2x squared plus 9. Ooh, how nice. Okay, minus. And then now when I distribute it to the second term in the numerator, the radical cancels out entirely. Perfect. And then the denominator, I can write it as 2x squared plus 9 to the 3/2, because this is to the first, to the 1/2, add the exponents. You're on your way. Good, good, good. We're almost there, almost there. So now just distribute in the numerator so we can combine some like terms. So 4x squared plus 9 minus 4x squared over 2x squared plus 9 to the 3/2. And then, oh, you know what? That should have been an 18. I was way too excited. My apologies. Then 4x squared cancels out, and you're just left with 18 over 2x squared plus 9 to the 3/2. Boom. There's our second derivative. Woohoo! We're not quite done. We needed also to find f double prime of 0. So that's going to be 18 over 0 plus 9 to the 3/2. So that's 18 over 9 to the 3/2. You take the square root of 9, that's 3. Then you raise it to the third power, that's 27. So 18 over 27, that reduces to 2/3. And then what else did they want from us? F double prime of 2. Okay. F double prime of 2 is 18 over 2 times 2 squared, that's 8, plus 9 to the 3/2. So this is 18 over 17 to the 3/2. That's not going to clean up cute, so I'm just going to leave it. Okay, good. You might want to write it 17 rad 17, but guess what? I don't want to write it like that, so we're just stopping here. Okay, now second derivative is very useful because it tells us something about our function and its concavity. If you haven't heard concavity before, I'm going to go over it briefly with you. So a graph can be either concave upward or concave downward. If you notice here, I'm just showing like a little portion of a graph, and on this portion, it's concave upward. If you look, all of these little tangent lines are increasing in their slope as you move from left to right, concave up. Here, this is an example of a piece of a graph that's concave down. And if you'll notice, all of these tangent lines, their slopes are decreasing. Another way to help you remember what the shape would look like is concave up is like a cup that can hold something. Concave down is like a frown, sad face, sad face. And a graph can switch from being concave up to concave down and vice versa multiple times. Where that switch occurs is called an inflection point, when there's a change in concavity. So why are we talking about concavity? Well, we just learned how to take higher order derivatives, and the second derivative can give us information about the concavity of a graph. So suppose a function f has a first and second derivative at each point in an open interval. If the second derivative f double prime of x is positive, it's greater than 0, for each x in the interval, then f is concave upward. If f double prime of x is negative, less than 0, then f is concave downward on that interval. So when we look at the sign of the second derivative, it'll tell us whether or not the graph is concave up or concave down on that interval. Let's just look at an example here without actually computing the second derivative, but just make sure that graphically we can identify the concavity correctly. So find the open intervals where the function is concave upward or concave downward. And then find any inflection points. Remember, that's where there's a change in concavity. So this looks sad to me, down like a frown. So the graph is concave down from negative infinity up until here, where x is -2. Then it switches. This is concave up, like a cup. See how it could hold a nice glass of water for you? And then it switches again, concave down like a frown at 6. So let's list the open intervals. Where's the graph concave down from negative infinity to -2, union 6 to infinity? It's very common. You can just abbreviate concave down, CD, okay? Concave up, you can also abbreviate that CU. It's very common. Concave up from -2 to +6. Are there any inflection points? Remember, inflection points is where there's a change in concavity. Yes, I have 2 of them. F of -2, which is -4, and then f of 6, which is -1. Beautiful. Now, most of the time, you're not going to be given the graph. You're going to have to go ahead, find the inflection points on your own. So let's try that. Here we go. Find the open intervals where the functions are concave upward or concave downward, and then find any inflection points. And just like when we were finding where a function was increasing, decreasing, and its extrema, we list the domain first. Do that as well here, because if there's a domain restriction, that can't be an inflection point. Okay, so first example, f of x is 3 minus x to the 4th. So this is just a polynomial. The domain's all real numbers. I'm going to go ahead, take 2 derivatives, right? You need the second derivative for inflection points and concavity. So first derivative, f prime of x, we got to use the chain rule. Bring the 4 down front, and then you have 3 minus x cubed. And then don't forget, you got to multiply by the derivative of what's inside, which is -1. So this is -4 times 3 minus x cubed. Okay, one more time. So f double prime of x is going to be -12 times 3 minus x squared times another -1. So now this is +12 times 3 minus x squared. Okay, there's my second derivative. Now, I want to find where the second derivative is positive and where it's negative. So much like when we were finding critical values, I want to know where f double prime of x is equal to 0 and where f double prime of x does not exist. Where does it equal 0? Well, ignore this 12. This will be 0 if x is 3. Doesn't exist, that doesn't happen because this is a polynomial. Okay, then again, you're going to make a number line. This should feel very familiar. It's just now we're doing everything with the second derivative because we're interested in concavity. And I put my one possible inflection point on there, 3. And then we're going to test into the second derivative the sign of some x value in each of these intervals. So pick something smaller than 3, say 0. 3 minus 0 squared, that's going to be positive. In fact, I don't even need to really plug anything in. This is positive, This is squared. It's positive, positive. Put a little happy face, happy parabola, or a cup to remind you it's concave up. So the graph is concave up where? From negative infinity to 3, union 3 to infinity. You got to skip over the 3. You can't just say negative infinity to infinity. You'd be a liar. Because at 3, the graph is not concave up. The second derivative is 0. Are there any inflection points? No. Is it concave down anywhere? No. So if you want to write concave down nowhere, you can. It's not needed. And then no inflection points. Okay, good. All right, let's try another one. Here we have f of x equals 2 times e to the negative x squared. So any domain restrictions, e to the negative x squared, no, we can plug in anything. We're good to go. Okay, so domains, all real numbers. Let's take two derivatives. So f prime of x, again, we need the chain rule. So 2 times derivative of e to the something is e to the something. And then I have to multiply by the derivative of the something, which is negative 2x. So this is going to be negative 4x e to the negative x squared. Yes? Okay, now I need a second derivative. So this time we have to do the product rule, right? We have two functions. Here's 1, here's 2. So product rule time. Derivative of negative 4x is negative 4. Then leave e to the negative x squared alone. Plus, now I leave negative 4x alone, and then derivative of e to the negative x squared is e to the negative x squared times negative 2x. Good. Okay, let's see what I can factor out from both of these terms. What do they have in common? They've got e to the negative x squared in common, and they've got a negative 4 in common. Okay. So negative 4 e to the negative x squared. I'm just going to have a 1 left over here. And then what's left in that second term? X and negative 2x. Okay, so minus 2x squared. This is my second derivative. Again, I want to see where does f double prime of x equal 0 and where does f double prime of x not exist. All those values are going to get listed on my number line. So the derivative equals 0 if either of these factors is 0. So if negative 4 e to the negative x squared is 0, or if 1 minus 2x squared is 0. So negative 4 e to the negative x squared is 0. That means e to the negative x squared is 0. But that's never going to happen. You can't take e, raise it to some number, and get 0. That's impossible. So none. What about 1 minus 2x squared is 0? That would mean 2x squared is 1. So x squared is a half. So x equals plus or minus 1 over rad 2. Okay. Doesn't exist, none. The domain's all real numbers still. So here we're going to make our number line. Label it so you don't get jumbled up, because we're going to build on what we did in the last lesson and put everything all together soon. So label each of your number lines. This is f double prime, and I'm going to have negative 1 over rad 2, 1 over rad 2 on there. If you want to plug it in your calculator, just so you know for testing, this is about negative 0.71, and then this is positive 0.71. So I'm plugging into the second derivative, like say negative 1, okay? I know e to whatever is not going to be negative. So this is always negative right here. This is always negative. And then I have 1 minus 2 times negative 1 squared. 1 minus 2, that's negative. So negative times negative means the second derivative is positive here. So the graph's concave up. If I plug in 0, remember this is always negative. 1 minus 0, positive. Negative times a positive, that's negative. And then something bigger, like positive 1. This will be negative. This is negative. So second derivative is positive. Concave up. Ooh, so much is happening. Okay. So let's summarize. Let me just add in some space here, you know. We can't be expected to do math properly when we're squished. So the graph is concave up from negative infinity to negative 1 over rad 2 union 1 over rad 2 to positive infinity. concave down from negative 1 over rad 2 to 1 over rad 2. And are there any inflection points? Why, yes. F of negative 1 over rad 2. This goes back in the original function. Do you remember what the original function was? If you forgot, allow me to remind you. F of x was 2e to the negative x squared. So if I plug in negative 1 over rad 2, I square it, it's 1/2. So I have e to the negative 1/2. And then that 2 out front. And you know what? You're going to get the same function value if you plugged in positive 1 over rad 2. Okay, good. So now we're able to identify intervals of concavity using the second derivative. The second derivative also can tell us whether or not a critical value is a local min or max. And you might say, what are you talking about, Professor V? I thought mins and maxes we use the first derivative for. You can. That's our first derivative test with the number line. But we have another option called the second derivative test. So here's how it works. First, we got to make sure this second derivative exists on some open interval containing c, and let f prime of c equal 0. So that means c is a critical value for f. If f double prime, the second derivative, is positive, then f of c is a relative min. Let's think back to what we just learned. This tells me the graph is concave up when the second derivative is positive. And I already know the derivative is 0. That means the slope of the tangent line is 0 at c. Well, then clearly you can see if the graph is concave up and the slope of the tangent line is 0, that only happens if c is a relative min. And then similarly, if the second derivative is negative, then f of c is a relative max. Second derivative being negative means the graph is concave down. I already know f prime of c is 0, horizontal tangent line. That only works if f of c is a relative max. So basically this gives you a way to identify where you have a relative min or max without having to make the number line for the first derivative. It's pretty good. The only time that it's not useful is this third case. If the second derivative is 0 or it doesn't exist at c, then the test gives no information and you've got to use the first derivative test anyways. So if we're being perfectly honest, I only use the second derivative test in certain applications like word problems. Usually if I'm asked to find all of the relative extrema, I still do the first derivative test because I know it's going to give me the info that I need every single time. Second derivative test is nice on one-off situations, okay? But let's just practice it. Example says, find any critical numbers for f and then use the second derivative test to decide whether the critical numbers lead to relative maxima or minima. So since they told us to use the second derivative test, we got to be obedient. So here we go. First, let's list the domain. It's all real numbers. And let's find the critical numbers. Remember, that comes from where the derivative is 0 or doesn't exist. So f prime of x is going to be 6x squared minus 8x. Let's see, where's f prime of x equals 0? If 6x squared minus 8x is 0. So I can factor out a 2x, and I have 3x minus 4, right? So that's when x is 0 or x is 4/3. And then is there anywhere the derivative doesn't exist? Well, no. But just always think about it, okay? Just think about it. And then now we're going to, instead of making the number line, we're going to take the second derivative. So f double prime of x is going to be 12x minus 8. I'm going to plug in each of the critical numbers for x in my second derivative. So f double prime of 0 is 12 times 0 minus 8. That's negative 8. So since the second derivative is negative, the graph is concave down there. And I already know since the first derivative is 0, the tangent line is horizontal. And that means f of 0 is a relative max. What's f of 0? It's just 2. Let me tell the people all the info. It's a relative max because the second derivative was negative. The graph is concave down. That only happens if the critical value is a max. Okay, other critical value, 4/3. So f double prime of 4/3 is going to be 12 times 4/3 minus 8. That's 16 minus 8. That's positive. You don't care what number it is. You just want to know if it's positive or negative. So that tells me the graph's concave up. We're at that critical value, which means, yes, we have a relative min. F of 4/3, whatever it is, I don't feel like plugging it in, is a relative min. Okay, so that's how the second derivative test works. It worked out nicely for us here. Okay, now let's look at an application into economics, namely the law of diminishing returns. And it tells us about a point where there's a smaller and smaller return for each dollar invested. So basically, the law of diminishing returns is related to the idea of concavity, in that the inflection point at C, f of C, is called the point of diminishing returns. And if you go past this point, then there's a smaller and smaller return for each dollar invested. You still get a return on your investment, but not as much as you were up to that point of diminishing returns, the inflection point, okay? So here is an example. Find the point of diminishing returns for the given function where R of X represents revenue in thousands of dollars and X represents the amount spent on advertising. Okay, so this is giving us revenue based on how much you're spending putting ads out. And here's our revenue function, R of X equals negative 0.3x cubed plus x squared plus 11.4x. And we're only looking at x values between 0 and 6. So as soon as you see they want the point of diminishing returns, you go up, they want the inflection point. So I need to take two derivatives. So first derivative, r prime of x is negative 0.9x squared plus 2x plus 11.4. And keep it going, one more, round 2. R double prime of x is going to be negative 1.8x plus 2. Okay, so to find the inflection point, first I need to see where r double prime is 0 and where r double prime does not exist. It exists everywhere, so I'm not going to get any from here. But let me set negative 1.8x plus 2 equal to 0. That means negative 1.8x equals negative 2. And then just round to however many decimals your instructor tells you. I'll just round to 2, but they should be specific, okay? 1.11. Okay, so let's see here. I'm going to make a number line, but I'm not going to put arrows on it because we're only interested in values between 0 and 6, remember? But that's fine because 1.11 lies between those. So say we plug in 1 here, that'll be positive, so the graph's concave up. And then if I plug in like 2, 3, yep, negative. So it's concave down. Perfect. So that's the point of diminishing returns. That's my inflection point. So R of 1.11, always plug it into the original function. When they ask you for the point, they want the point on the original graph, R of X. It comes out to about 13.5. So if you were to plot it on the graph, it'd be like 1.11, comma 13.5. And remember, we have units here. So R of X is revenue in thousands. So this is in thousands. And X also represents amount spent on advertising in thousands. So that means once you've spent basically $1,111, you get $13,500 in revenue. And then if you start spending any more than that, you won't get as much revenue for your additional advertising costs, okay? You'll still get an increase in revenue, but not at the same rate that you were up to the first $1,111. So kind of up to you. Do you want to keep advertising or not? Maybe you should consult with your financial analyst. All right, so that concludes the lesson. Give it a thumbs up, subscribe if you haven't already, and stay tuned. We're going to get into curve sketching soon. Very exciting stuff. And if you need to review anything, you can always check out the video lectures organized into playlists on the rest of my YouTube channel. Follow me on Instagram and TikTok, Math with Professor V. I'll be back soon.